Welcome to The Explainer. Today we're digging into a pretty radical idea, a theory that claims it's found one single mathematical key to unlock problems in fields as wildly different as hypersonic flight, finance, and even medicine.
It sounds like science fiction, right? The idea that one single mathematical engine could be tuned to tackle problems in completely separate worlds, from the insane heat of hypersonic flight to the chaos of the financial markets, and even to the clarity of a medical scan? Well, that's the powerful premise we're exploring today.
So here's the core challenge in modern science and engineering. It's all become incredibly specialized. Each field, whether it's aerodynamics, quantum physics, or finance, has basically developed its own unique mathematical language, its own set of complicated equations that are tailor-made for its specific problems.
Just look at these two. On one hand, you've got these incredibly complex models for how air flows over a jet. On the other, equations for pricing a financial option on Wall Street. They're both trying to figure out complex systems, but they're written in completely different mathematical languages. This makes it so hard to share insights of tools. It's kind of like having a room full of brilliant engineers who can't speak to each other.
Okay, so this is where a breakthrough called WaveCore Continuum Theory, or WCCT, steps onto the scene. It proposes a pretty wild solution, a single, elegant mathematical engine that can act as a universal translator. You know, like a mathematical Swiss Army knife for all of science.
And this is it. This is the core equation of WCT. Now, at first glance, it looks deceptively simple, right? But contained within this really elegant structure is a remarkable versatility. This isn't just one equation for one problem. Think of it more like a blueprint for countless different solutions.
So, how can one little equation do so much? Well, the magic is in what you could call its tuning knobs. The variable phi, for instance, can represent a pressure field in fluids, or it could be a stress field in materials. Rho can be the force acting on a system, or it could just be the data coming in from a sensor. And m squared and lambda, those are the master controls that let you adapt the equation's behavior to pretty much any specific domain you can think of.
But look, the power of WCCT isn't just that it's flexible. It's that this flexibility is built on a rock-solid foundation of mathematical guarantees. This isn't just some clever party trick. It's provably reliable, which is absolutely crucial when you're talking about mission-critical applications.
So where does that reliability come from? From a series of mathematical proofs called lemmas. And you can totally think of a lemma as a proven mini-theorem that acts as a building block for a bigger result. In this case, they're kind of like the certified safety checks or the building codes for the entire theory, making sure that any solution you build with it is stable and totally trustworthy.
And here's how those lemmas provide a safety net. First up, Lemma 1 guarantees that a solution actually exists, so you're not chasing a ghost. Then, Lemma 2 makes sure that solution is stable. It won't just spiral out of control and, blow up. Finally, Lemma 5 guarantees that the computer simulation is accurate. You put them all together and you've got a tool you can actually trust for really important jobs.
Okay, theory is one thing, but what does this actually look like in the real world? Let's take a quick tour of a few early prototypes to see just how broad the applications of this single tool can really be.
All right, first stop, the U.S. Air Force Research Lab. They're facing this massive challenge with hypersonic flight, how to control the insanely complex airflow over a scramjet. If you get it wrong, you're looking at catastrophic engine failure.
So, they put WCCT to the test. As you can see, the domain here was hypersonics. The goal? To knock down the prediction error by at least 10%. And the result? They achieved a 20% error reduction, doubling their target. This is a perfect example of how better math leads directly to safer, more reliable designs.
Okay, now for a total change of scenery. Medical imaging. Low-dose CT scans are, of course, safer for patients, but the trade-off is they often produce noisy images with these streak artifacts that can hide really important details. So, could the same math help here? And check this out. The goal here was to use WCCT to clean up those streak artifacts you see in the noisy scans. The result was a massive 75% reduction in that specific error. Just think about what that means. A dramatic improvement in image quality, which could lead to much more accurate diagnoses from safer, lower-dose scans.
All right, from healthcare, we jump to the high-stakes world of finance.
Pricing complex financial products, things called options, is notoriously difficult, especially when markets make sudden, unpredictable jumps. The traditional models often just can't keep up.
Just look at this comparison. The standard industry model had a pricing error of about 10%. By adapting that same WCCT core, the new model slashed that error all the way down to just 2%. In finance, that's the difference between a risky bet and a well-informed decision, and it all comes from the same core equation we saw just a few minutes ago. It's incredible.
Now, these examples are super impressive on their own, but the real vision behind WCCT is even bigger. This isn't just about solving individual problems one at a time. It's about creating a unified platform for innovation.
And this, right here, is where the true power lies. When everyone starts speaking the same mathematical language, amazing things can happen. You get cross-domain synergy, where a breakthrough in, say, turbulence modeling could suddenly help someone in materials science. You can go from experiment to simulation way, way faster. And the whole system is incredibly scalable. It'll run on anything from a tiny Raspberry Pi to a massive supercomputer.
As the researchers who developed it put it, WCTT isn't just another tool. It's a meta-platform. It's a foundational framework for modeling, predicting, and optimizing pretty much any system that's driven by the kinds of wave-like phenomena that are so fundamental to our universe.
And that leaves us with a fascinating final thought. For centuries, scientific disciplines have evolved in their own silos, each developing their own private language. If a tool like WCT can truly act as a universal translator, it just begs the question, when all of science starts speaking the same language, what incredible new conversations are going to begin, and what discoveries will they unlock?